Pleasure to have Kostas Alexis here. He got his PhD from University of Patras in Greece, and after that was at ETH Zurich for 4 years as a senior researcher working on autonomy. And I think one of the things that he's kind of famous for is also the solar soaring for extended times. And since July 2015, he's at the University of Nevada, Reno, and he'll tell us a lot about exploration and mapping with real world. Thanks for.
Thank you. So thanks for hosting me, first of all. Thanks for attending the lecture and to have the opportunity to meet some of you, and hopefully I will talk with more of you after the seminar talk. So as Sebastian said, today I'm going to discuss about autonomous exploration and mapping. I'm now at my new lab. I call it Autonomous Robots Lab, essentially also describing what I am for in my life, contributing to this direction that many of you also contribute to make robots autonomous and be able to do something great for the society. I don't think I have to convince people like you about why robotics are cool and great, but I want to share with you the fact that I try to read one book of Asimov every year to keep my motivation high about what robots should be able to do, and we are still not able to do because our technical capabilities are still not there. There are many things missing in terms of control, perception, planning, intelligence, but also many things are on the way so that such robotic systems could become a reality at some point. If some of you haven't ever read the book of Asimov, I propose this book, Robot Visions. It's the reason to do a robotics PhD. The particular motivation for this talk is relatively obvious. Most of the times, aerial robotics are used for inspection and exploration. That's the primary task, either for monitoring, surveillance, 3D mapping, detection of change, detection of a particular area of interest or an object. There are many, many applications related with inspection, exploration, and mapping. And of course, there are necessities to achieve something like this related with controls, so how robust the robot is flying. Controls in a more broader perspective, so how the robot essentially employs feedback to achieve a certain action. Localization, mapping, all the perceptual capabilities of robotics. And of course, path planning, an extension essentially of the broader field of control to achieve applications like finding the coverage path or the exploration path for robotics. I started working in the field of exploration and mapping, inspection, the last 3 years. And my motivation since then was what one can describe as active perception. So robots that essentially actively employ their currently perceptual capabilities, their onboard localization, real-time localization and mapping to decide what's the best next action to do for exploration or inspection. Of course, I started with simpler methods from those that appeared later from my work and the work of my students. And I will go through the process of this research the last 2.5 years. The second goal from the beginning was to open source what we are doing. The idea is that, at least from the side of this work, we can contribute methods that others can use, and not only use because they might be the best. Of course, better research will come from many, many people, but this way also they can evaluate their work in comparison with what we are doing and hopefully outperformance in many, many ways, and demonstrate that with essentially fair evaluation, and this hopefully leads to better and more systematic progress. And the third goal was to simultaneously, whatever we do as good field studies, also a reason why I admire your university about doing a lot of field evaluation of robotic systems, to also release data sets so that people can see and compare how we achieve, what is the actual performance of our methods, and then use these data sets, both the processed and the raw data, to compare their own methods in a very systematic way. Walking through this progress of research, of course, everybody wants to deal with all the challenges involved, either in terms of the robotic configuration, and I have primarily worked with multi-rotor systems and fixed-wing UAVs. The one on the right is the one that Sebastian mentioned, is a 5.6-meter wingspan UAV with many, many people that worked in Zurich for this project. It achieved 81.5 hours of continuous flight by charging during the day using solar panels, crossing the night sustainably, and charging again the next dawn, and so on and so forth. We demonstrate that during July, so we can't do it any time of the year at the moment, but hopefully this will become possible. So dealing with the configuration is one challenge. Dealing with environment is another major challenge. Either it is an artificial environment, made by people like an oil and gas industry, physical environments like a forest, or very difficult environments like a tunnel that is dark, visually degraded, and many of you also probably work in this direction. So the whole goal is to do autonomous exploration and mapping for virtually any robot and virtually any environment. That's at least the motivation. Now, naturally, once somebody discusses about exploration and mapping, it might refer to the case that the robot has no knowledge about its environment, or it might refer to the case that the robot has some complete or partial knowledge about its environment. It might refer to the case that it essentially the human might be there or not be there. It might be purely a global path computed a priori, so you can't exploit the statistics of the real-time localization and mapping process. And of course, it's also related with what kind of robot you are using. So we have proposed a library, an ensemble of methods that addresses many of these problems in one or the other way. And hopefully we can also compare among the methods we are developing on our own. The assumed robot configuration, and I will come also to the particularities of that for different experiments, is quite obvious. So we consider a robot, it has its own locomotion capabilities, able to fly, for example, one or the other particular way, holonomic or non-holonomic trajectories. We assume that we have a good guidance and control system, and I believe that's something that one can assume at the moment. There has been a lot of work from the community to even open source good controllers for many robots, or there is also a lot of good commercial solution for this problem. And then there are two main blocks, the localization and mapping system, as well as the path planning module. And the great idea is essentially, or what we are trying for, is to put that together and unify their design as much as possible. Instead of the classical separation approach, try to unify their design. This is our recent work that we also did the last 8 months in Nevada, and previous work essentially allowed us to go towards this goal. The particular configuration, for example, for the latest robot we developed is this one, but it's very relevant with all the robots that I have worked with. There is a low-level autopilot, either the Pixoc system developed at ETH, or it might be a commercial solution. There is a position controller, either running on the embedded system or running on a high-level controller. For us, a linear model predictive control most of the times, or a non-linear model predictive control at the moment. There is a stereo visual inertial system, but you can also consider it in general a localization and mapping pipeline that provides the robot pose, the robot state, and for example, the track landmarks or other methods like dense mapping and so on and so forth. And on top of that, we have the path planning module, and the idea is to essentially to try to see how we can do autonomous exploration by exploiting the feedback from the localization pipeline. So starting from the first case where the robot has absolutely no idea about its environment, so it's agnostic to the environment, and the only thing that knows about the environment is that it is bounded within a certain volume, and it's worth exploring it. So the first way we approach this problem is the purely geometric way. So we just care to find a set of viewpoints that will allow us to explore all the environment without having prior knowledge about it. And of course, this will be subject to the robot constraints, the robot motion model, and there are, of course, the sensor model and its capabilities to map the environment. And there will be cases that we can't inspect certain parts of the environment because there might not be any admissible robot essentially configuration to perceive the environment. But apart from this, unable to be explored space, because you might have a fixed wing system that cannot navigate within a certain volume to find all viewpoints, the goal is to essentially guarantee full exploration of the unknown volume. As mentioned, I started my work in robotics coming from controls. So when I searched the literature, I saw this work on frontier exploration and several stuff like that. And my idea was to use 3 basic ideas that existed beforehand in other fields. One of them is the next best view sampling. Find the next best view to 3D model an object, number 1. Number 2, use sampling-based methods in motion planning that were developed, for example, for collision avoidance and optimal collision avoidance with RRT star and so on and so forth. And the third idea was to use receding horizon approaches that exist in control theory, and they tend to robustify the performance of the controller. Since they predict further, they act only for 1 step ahead, and then they reevaluate the trajectory of the control actions for the trajectory of the robot. So the key idea was to use these 3 basic concepts, combine them together for the problem of exploration. So how do we do that? We assume that the robot knows nothing initially apart from a very limited space around it. So it just exists, the robot exists in a very small part of the world. In this existing world, of course, it can sample configurations. If it knows absolutely nothing, it can at least yaw around its own self, right? That's the basic idea. Within the currently known world, we can sample a tree of next configurations, and the assumption here is that we do have a boundary value solver. So if we go from point A to B, we can find the trajectory to go from point A to B. But of course, if you don't like that, and if you think that this is limiting to the method, then you can also recast the problem to control space sampling. But overall, we can sample a tree. We can span a tree in the known configuration space. Now, at every vertex of the tree, naturally, we can annotate the viewpoint for a particular sensing modality. We might have a camera with an oblique configuration and this and that horizontal and vertical field of view. Now, as you annotate every vertex with this information, you can cast and find which of the branches of this tree has the maximum information gain in terms of how much volume is going to be explored if I follow all these branches. Pretty simple idea. All these ideas here are very simple. And then once we evaluate this best branch, we are going to only execute the first step and then reiterate for the next time the whole procedure by updating the map in between. So now the robot can plan more in a larger space because it spanned and explored a large part of the volume through its localization and mapping pipeline. There is a small factor at the end for those that potentially see it and wonder that just tries to penalize arbitrarily long paths in the currently known space. So essentially we have the tendency to employ shorter paths as we sample further in time. The considered representation of the world is an octomap, an occupancy map. I'm sure you are familiar with the terminology. And we are using this representation both to map the world, it's memory efficient, and also to conduct collision checking. It's pretty obvious, so we don't have to say much about that. And essentially, the localization and mapping unit provides this as a feedback to the planner. So the planner is actually a controller about what are the next viewpoints of the system. As mentioned, it's using the spanning tree. It spans a random tree to find configurations which allow us, given that we allow sufficient depth to the tree, to find all viewpoints that we need. We limit the amount of iterations, so we have a finite depth system, unless the system doesn't find any best configuration, so we keep iterating inside the while loop. Once we evaluate which branch is the best, again, summarizing here, conduct the first step and redo it. So if you had to write this thing in terms of pseudocode, it will be as simple as this one page. We start from considering that our current configuration obviously doesn't lead to further exploration gain. We span the tree, we evaluate branches about which of them is the highest information gain, we select the best, we conduct the first step, and we reiterate the process. So it's very simple as an idea. The question is it better from what was there before, for example, from frontier-based methods? So the first question there is, okay, we are doing more stuff compared to another method, like a geometric exploration, and is it still sufficiently computationally lightweight? And building the tree is lightweight, conducting collision checking inside the octomap is lightweight, and performing the computation gain for the information gain I described is also very lightweight. And also, the fact that we span a tree of finite depth, essentially it also scales with how much large volume we have and what's the resolution of the octomap we are going to employ accordingly. So overall, we have a couple of milliseconds, 2 or 3, per iteration for an environment like this size if we were to span trajectories within that and evaluate what is the best next move for the robot to explore the unknown volume. So before we went to the experimental evaluation, we first did this study, among others, in simulation to essentially explore the bridge in comparison with frontier-based exploration. Now I have to say we implemented this one. It's not open source. So if we did something worse in implementation, it's possible. However, conceptually, I think we captured the fact that we converge faster to the exploration solution, and we actually explore the whole space, whereas when the environment is complex, frontier-based exploration struggles to find the next view at some point to explore the remaining of the space. So that was an advantage in terms of that we explore faster and we still are computationally lightweight. We also did an extension to that, and once we have an exploration of the environment volumetrically, we thought that we can recast the information gain, and now instead of identifying new volume, let's identify how much surface are we going to explore, so what's the subset of the surface manifold to be explored. And you can do a second mission with similar convergence characteristics that explore surfaces instead of volumes. So experimentally, this allowed us to run an experiment in an environment. Everything is going to be GPS denied and also not support from Vicon. You will see Vicon markers, but it's for safety, or you have to believe in that it's for safety. The system employs the stereo visual inertial system that you saw in front of there. So it's a time synchronized stereo system, synchronized also with an IMU, developed at ETH in Zurich. And this is essentially what allows the robot to perform localization and mapping, and then based on the dense point cloud from the stereo system, also run the octomap and also have a dense map at the end to provide us an end result to the end user of the work. So once the robot starts in the unknown environment, I believe that if I ask you what will you do if you enter a new unknown space, the first thing you will do, you will look around with your head. It doesn't cost you much about your control actions, and it is an efficient way to explore around you. So this is also luckily what the robot does once you leave it to explore the unknown space. It doesn't know much of the environment, so it can't span any trees all around. And it finds that the short trajectory to explore a lot is this very simple thing, just yaw around. right? Now, is this necessarily the best thing to do? Well, if you have a monocular system, that's probably a nice way to break your localization system. So we will go to all these uncertainty things in the next work. But this system here will map this world with this volumetric presentation, find trajectories in that, and keep exploring until it finds that there is no configuration that will potentially lead to better or further exploration of the space. Now note that this is a probabilistic presentation on the backend, so every voxel here has an occupancy, and there's a probability associated with this being occluded or not occluded, and naturally, of course, as long as there is no global mapping solution, the system will potentially still try to find new viewpoints because some voxels change from occupied to free. What you see here is the real-time dense mapping of the environment using the robot. So that's result number 1. And there are some instances of this result that you saw in real time, so there is no need to go through that. This algorithm is open source, and I will come to the open source also packages at the end of my lecture, so you can potentially, if you like something, you can also use it as a ROS package that you can just install. Now the next phase was to consider the fact that just selecting viewpoints to explore an environment doesn't mean necessarily much about how well you explore an environment, how well you map an environment. And the order of observations, the observations you select and their order will influence how well you are doing localization and mapping, right? So you can't just say, I'm going to select a set of viewpoints and run them afterwards and expect necessarily a good map. So our next work, which we did here with my new team in the States, was to solve the problem of using belief space propagation for better exploration and mapping of unknown volumes. But we thought that instead of putting these two problems together in some sort of additive objective function, we will solve them in 2 steps, like a nested optimization. The first layer will ensure efficient exploration, and only once efficient exploration is ensured, then we are going to go further to see if we can minimize the uncertainty of the robot. Therefore, we aim not to compromise the exploratory behavior of the robot demonstrated in the previous work. And also, I believe it's better to do it this way. It's also pretty a known concept in control optimization to do nest optimization rather than just adding terms in a large objective function that ends up being without a specific meaning. So we consider the configuration that I mentioned initially. The key thing here is that we are using a stereo visual inertial system. You can use something else. Something, however, that gives you the pose and the state of your robot as well as the track landmarks, one way or the other. So the 2 layers will be the first one, and there is a small modification in the first layer which does essentially what the previous algorithm is doing. Receding horizon, next best view to find the next viewpoint to follow to explore the space. There is one modification in the information gain, and I will come to that later. And then the second step, once the first step has defined where is the next viewpoint to go for exploration, it will try to see what's the best trajectory to follow in order to minimize the uncertainty at the end final configuration about the robot's pose and the track landmarks. And of course, we do that for all admissible paths that are spanned and arrive to the final destination. To also shorten the problem and decrease the size of the problem a bit, we also consider a limited volume around the initial and the final configuration for the robot. And we allow, we consider an admissible trajectory, a trajectory that starts from point A, goes to the final configuration there, and is not significantly larger from the straight line, right? So the first step is what I mentioned. That's just a visualization for you to recall. So we span tree, we select the best branch, and we are going to conduct only the first step and redo the process with the updated map in a receding horizon fashion. The only change in the information gain that we are using is this addition of what we call reobservation. And this employs the fact that the octomap, on the back end, there is a probability associated with every voxel for it being occupied or not occupied. So as long as these probabilities are low, and what you see here as purple and blue means low probability, then we consider worth to reobserve. Now I know, and that you might come with a criticism, that you are not doing a global consistent map solution, so these voxels might change for no purpose. This is true. This means that this performs well locally, and as long as you're going to use it over large scales, large volumes, and large experiments in a global sense, you should have a more consistent, more global mapping and localization solution. Now, in the second step, which is the important contribution compared to the previous algorithm, is what we're doing here. We span these trajectories that start from where the robot is, and all of them go to the configuration selected from the previous layer. But they go with different ways, from different paths with different state trajectories of the robot, for example, the ambient trajectories of the robot, and by viewing different parts of the environment. Now, the known environment, we will also have the currently tracked landmarks. For example, we are using a stereo visual system, then we track the latest 35 landmarks. That's a number. You can also increase or decrease based on computational capabilities. For every viewpoint that goes, as the system goes to the final configuration, we are able to evaluate which of these landmarks are going to be observable from the trajectory of the robot, and also for every sample of this trajectory. And therefore, we are able to estimate which landmarks are going to reobserve. And from that, since we have the statistics, hopefully we will be able to run in real time, or online at least, Kalman filters that will allow us to propagate the robot belief about the pose and the track landmarks. And we do so, we employ a robocentric representation of the robot state, which means that essentially we have R and Q representing the state. We have the biases, of course, because we also have to estimate the biases. And we also have the track landmarks. And this particular state applies to our work. But of course, for another representation of your localization system, this might be a bit different. What we want at the end for the algorithms to work is a covariance matrix that gives you the covariance for the pose and the track landmarks. And you might very well just change to another odometry pipeline. So we're having this state, which again, the important thing is the robot pose and the track landmarks. And naturally, I'm sure you're familiar with Kalman filtering and extended Kalman filtering. We are going to run two steps: a prediction step that considers the IMU trajectories, essentially the rotation acceleration trajectories, as the robot goes from point A to point B over samples of this path that we have spanned before that goes to final configuration and all the admissible paths. We're going to do that by propagating the equations. This means that we had to identify initially a simple nonlinear model of our robot. That's pretty simple, however, and also pretty efficient to run in real time. We are going to have the previously tracked landmarks, and we're also going to propagate, of course, also those. And once we do that, we are going to perform the update step of the Kalman filter. I will come to that. But the first step is pretty obvious. This solely means forward propagation of equations. There's nothing much here. That's also pretty computationally low cost. The second step involves two processes. For every step of the path that we sample with a specific time sample there, which has to be, of course, sufficiently small, but also nicely tuned for your problem, we go and check which landmarks are going to be observable, because possibly some of them are occluded from the structure. That makes sense because you have a structure that might occlude because you are behind the wall and so on and so forth. So we select for every point in the path which landmarks are observable. For those that end up being observable, we conduct also the filter update step. And through that, we are able to get for every point of the path the covariance matrix of the robot state and the track landmarks. Now that means that we are able to go to the final configuration that we want to go and have an estimate about which of the possible admissible paths allow us to minimize the uncertainty of the robot, and hopefully through that aim to get a better mapping solution. Now what you see here is the robot performing casting to see which of these features are visible. And what you see here is a small bubble is the 1 sigma of the expectancy of the landmark being in the particular position. Now, once we have the covariance matrix, as you know, which means we have an ellipsoidal about our uncertainty. Now, even if we annotate every vertex with a covariance matrix, doesn't mean that we have a way to say which covariance matrix is better than the other. So we need to employ a tool from the theory of optimal experiment design to evaluate which of these particular covariance matrices are better than the other in terms of uncertainty. So there are many different formulations there: entropy, A optimality, D optimality, and so on and so forth. We are using D optimality for the purposes of how it converges, and also the fact that essentially reflects the maximization of the determinant of the information matrix, which is what we are using to say which way we minimize our uncertainty about the robot pose and track landmarks. So we call that the belief gain. So the second level of the planner will try essentially to minimize the uncertainty as factorized from this parameter there called belief gain over all the admissible trajectories that go from point A to the next best exploratory viewpoint sampled from the first level of path planning module. So writing this algorithm also is pretty simple. Essentially, we run the first step that does exactly what we did before in the previous algorithm. At the end of the day, we get for this iteration the next best configuration, and we're going to use this configuration to guide the second level of planner to find admissible trajectories that start from this point to go to this configuration. Of course, we start by propagating the belief along the straight trajectory, because there is no reason to consider that necessarily a failure. So it might end up being the best, so we still keep it as a possibility. And then we sample a finite depth tree, finding a finite amount of possible trajectories. We propagate the belief, the way I mentioned before, along all the admissible trajectories, and we evaluate which of them seems to minimize the robot uncertainty about its pose and track landmarks at the final configuration. The computational complexity, I'm sure you expect it to be much higher. The critical question is it online, right? Because being more doesn't mean that's necessarily a limitation factor. So step by step or component by component, RRT construction is pretty fast always. Collision checking in the Octomap also pretty fast, scales nicely with the depth and the ratio of the volume of each voxel. Finding the computation gain for the first level of planner is very lightweight, naturally just evaluation of volume over the Octomap. And the second layer naturally depends on the number of states. So that means how many states your robot has, the number of landmarks, how many landmarks you are tracking. So if you increase that a lot, it might end up being very heavy computationally, and how often you sample your trajectory. So as long as this last component remains computationally tractable, then the whole system remains computationally tractable. So we found that we can run for a volume like our experiment was 12 meter by 6.5 by 2 meter high. We can run this algorithm in approximately 80 to 90 milliseconds, which means that since it's the high level task and not something like the low level controls of the system, 80 to 90 milliseconds is pretty low for a system, and it is affordable to use it in real time. So again, a reminder of the system and how it looked regarding the internals, and this is the experiment we conducted. So the robot starts from this space and uses the stereo-visual inertial system, starts exploring the trajectory. With blue, you see the exploration, the first level of planning, and with red, you will see the second level of planning appearing. So it has this part of the world, and also samples, essentially to find the way to minimize the uncertainty about its pose and the localization accuracy of the robot. And then it will follow this trajectory. What was important to see is that straight trajectories are not always disregarded, and sometimes you see the robot to first turn its head towards landmarks that were considered to be robust, and then following the direction towards the viewpoint. This is the opposite from what you will expect from a robot just going straight. Now you can see many scenarios that this makes perfect sense. If I am, for example, a robot facing this white wall and I'm very close to it, it will be very wrong if I keep sliding with a stereo camera solution along this wall and then finally looking towards the direction I want to perceive, because this will probably break my localization system. So the idea is essentially to use this information, to have a system that breaks less and drifts less during the exploration and mapping process. And hopefully this is also what we demonstrated with our experiment. Now the volume is pretty large, so the experiment plays 10 times faster than reality, but at the end we get this relatively consistent volumetric presentation and this dense map of the world. Dataset is already open source, and code will come open source very soon. These are instances of the experiment: the initialization step, the exploration step, the belief uncertainty propagation step, the fact that a height map of Octomap is represented here, and here you see the probabilities. It's essentially a fused representation. The requirement to do many ray casting to see which features are observable from a current pose and towards the current selected configuration for viewpoint, and so on and so forth. We evaluated, although that's not a consistent evaluation, how visually appealing our maps are compared to a high definition camera processed with Pix4D and Vicon supported poses here, and of course you see a perfect, or close to perfect, point cloud, very dense and also very consistent, and also everything metric there is pretty concise. And here what you see is the real-time result from the robot. Of course it's not equally good, but we want to demonstrate essentially visually that it's a visually appealing result. So this is as long as autonomous exploration is considered, either treating the problems purely geometrically, so just finding a set of viewpoints that covers the whole space, or also considering the requirement, in my opinion, to perform belief propagation to maintain small uncertainty for the robot pose and the map. And hopefully, especially for large-scale experiments, this makes much more sense. Now, there are cases in real life that you might have a model, either because somebody designed this model in CAD systems, or because you performed one of these previous missions initially, and now you have a model that you can exploit. So as you have this problem, it ends up being just a question of coverage. Can I find a full coverage path in an efficient way? Now, coverage problems, although an old thing in robotics, they always end up being something that's computationally difficult to solve, but doesn't mean that's intractable or something like this. This is actually my first work in the field of planning, and when I initially started this path, I thought I would focus on optimality before we go to efficiency. So the idea was to use sampling-based methods to inspect, for example, a manifold. Now, if you use a tree here, and that's why most people use graphs, if you use a tree, then you can't make the turn around the inspection manifold if you consider this very simple problem, because wherever you sample a viewpoint there, you will wire it naturally towards the shortest path, which is the root. But if you sample a forest, a tree of trees, so at some vertices you break the tree and you sample a new tree from there, then you have a structure that will allow you to find all possible admissible points. And if you wire them and rewire them in a way that you don't break visibility, but you maintain visibility the way you do tree and root rewiring of the tree, then we also proved that we can have the optimal solution. We compared that with another work from Papadopoulos from MIT that essentially is also proves optimality for their case, and not to our surprise, we ended up being similarly slow. Even for small systems, we need a lot of computational, and for our algorithms at least, also a lot of memory to find a solution this way for the full coverage problem. So afterwards, we thought, all right, possibly that's a solution for demonstration of optimality. Maybe it has some academic merit, but it's not really useful for large-scale real-life problems. So we thought to change the problem and find an alternative way. This is just the robot performing one of these missions and mapping the world. But find a method that's computationally more lightweight, although we accepted that's going to be somehow suboptimal regarding the performance. And we also went to the literature, and we saw that most people, when they solved this problem, they followed a two-step process. Initially, they sample a finite amount of viewpoints by solving the art gallery problem. This leads to the minimum amount of viewpoints to cover the whole space. The art gallery problem is about where to put the guards to essentially cover and monitor, survey the whole art gallery. And then once they find these viewpoints, they find a traveling salesman's problem solution that minimizes the route around them. Now, there is no reason why you should care necessarily, in my opinion, about the amount of viewpoints, as long as you have a robot that takes a camera frame every, let's say, 1/30 frames. Because essentially, you get a big amount of viewpoints. What matters is the configuration of the viewpoints, number one. And number two, sampling the minimum amount of viewpoints, if you have a robot with kinematic constraints, doesn't mean that the overall path will end up being the minimal. Because kinematic constraints will also have an influence on how you solve the asymmetric now traveling salesman's problem. So what we did is a different way. We sample viewpoints as much as we need, but we try to arrange their configuration in space in ways that will lead to an optimization of the overall full coverage result. So the idea, before we go to the specifics, is simple. We load, for example, a mesh representation of the world or an optimal representation of the world. We sample initial viewpoint configuration, which is pretty naive. We just consider any mesh facet, and we sample one viewpoint per mesh facet in a position that this mesh facet is visible. Pretty simple. Then we find all possible collision-free paths that go from viewpoint to viewpoint by running RRT stars. And then we find the cost matrix, and we solve the TSP problem. Now, that's the initialization of the algorithm. Afterwards, the algorithm we try to resample, and I will come back to how we sample specifically. Then we'll recompute RRT stars, and then we'll resolve the traveling salesman's problem by using the Lin-Kernighan heuristic, which is pretty efficient to solve TSP problems. So, as mentioned, we are employing both meshes or optimal configurations. This version is open source. The other one is somehow got lost into the process of open sourcing. Of course, if you have a mesh facet, so it's a triangle, there is a certain part of the space that you can sample a viewpoint that has limited field of view and limited range, such that this mesh facet is visible. It's a non-convex problem, so it can lead to some additional computational cost. Therefore, if you have the mesh facet, we convexified this problem to end up being computationally more lightweight. You lose some stuff regarding the optimality of the selection of viewpoint, but you have a computationally more tractable problem, which for our case, since we already accepted we are not solving the optimal solution, it was good to go, and we opted for this solution instead of solving with a non-convex solver every time, because we actually have a lot of viewpoints for a reasonable structure with reasonable fidelity. Then the idea is that as you have a viewpoint, another viewpoint that covers different facets, why not trying to, at least in the neighborhood, while not breaking visibility, while maintaining the visibility of the faces you are discussing, to put them in a way that the cost to travel from one to the other ends up being smaller in average. Of course, there is no global reason why doing this local optimization there will lead to a global optimization in the final solution, especially for the case of kinematic solution or kinematic constraints. But again, this is an approach that we opted for some engineering tricks to see if the final solution will be good enough and better from what we saw before in practice. So we also perform this optimization, and we use a QB solver with some linear constraints to do so. As mentioned, we solve RRT stars, so there's nothing to say here. It's all work for others. We use the Lin-Kernighan heuristic, which essentially breaks connection paths and attempts another path to solve the TSP problem. And from that, we're able to find solutions. For example, for a subsampled version of Big Ben, I know it doesn't look like Big Ben, but it was the subsampled version of Big Ben there. We're able to find solutions pretty quickly. Actually, the computational cost there is mostly visualization, not really the algorithm execution. So we tested that first with a multicopter UAV, because it's the easiest thing to do. So we took off we are outside, but the robot flies in GPS-denied trajectories. We don't assume that we are using GPS, although it could very well also be used in the particular scenario here. It probably should be used since it's available. And this is the path we found to inspect these 4 truncated cone structures and avoid the obstacle that you see there as this garbage bin. That's pretty obvious looking experiment, so I'm not going to run it all because just the robot will go and navigate all the trajectories that you see there. What is important to say is that we do see that the real-time mapping is good. We also performed offline post-processing, and we see full coverage of the result without holes or something like this. And we also have open source both raw and processed data for you if you want to check. Now, what is more important for the full coverage problems is this case. What if we are able to explore larger volumes and map larger volumes? So we developed a plane. Many of my colleagues and myself worked on a project called AtlantikSolar. The idea was obviously to cross the Atlantic with a UAV. It's still to happen, but it's a great motivation to work all day. And then we thought we were going to make it lightweight to be able and small, so you have a hand-launchable UAV that flies for multiple days. Now, what is important is that although it sounds like a bit too much of an engineering effort, and it was maybe for a team, but at the end of the day, if you have a proper airframe, lightweight and properly dimensioned, solar panels that are efficient, and nowadays flexible solar panels, lightweight solar panels are efficient, a proper autopilot system that is robust, a power system regarding the batteries. We are using the same kind of battery that Tesla is using the Panasonic 18650, and essentially a charging system that is also efficient. We had to play a little bit with that. Then you can have the power efficiency required to fly during the day, charge sufficiently, cross the night sustainably, and recharge the next day. And then once you have that, you have an operational capability that is very different from most of the aerial robotic systems outside there. And you can also put your sensors, because you have a reasonably large now system that can carry quite a significant payload for many, many hours or days of operation. So the motivation was very specific. Large-scale systems, most of the times you can't afford them. It's not something that anybody, like any company, small company, will be able to afford. They are not versatile in their use. They require, significant infrastructure and maintenance to be used. And most of the times they fly above cloud coverage. So this means they can monitor and inspect and track and identify certain areas of interest on the ground. Whereas small UAVs, of course, they have all these nice properties of being flexible, but they fly for 1 hour if there is a fixed-wing UAV, 2 hours, maybe 3 hours maximum, but not more, most of them. And the motivation is be able to do all the below cloud coverage applications that are interesting to us, to society, for surveillance, monitoring, inspection, and you name it. But at the end of the day, do it with a flexible UAV that still flies for many, many hours or days. The aircraft was 5.6 meter wingspan, so sizable, but still one person is able to take it with his hand and then shoot it for a hand launch procedure. 6.9 kilos, so it remains lightweight. Half of it is batteries, by the way. The rest is some electronics and the structure and so on and so forth. And overall, a versatile system. All the wings are covered with solar panels. Batteries are distributed across the wing in order to have a nice properties of inertia. Naturally, MPPT trackers, PowerPoint trackers are custom designed for one of our engineers there at ETH. And then the power system, the batteries supplying with a unified power bus, the autopilot, the camera systems, it has the same now monocular inertial system instead of stereo. I believe that now some of my colleagues there are considering using stereo systems for the fixed wing UAV. Communication channels are multiple, also a SATCOM communication because you are expected to fly for many hours in places. Robust servos, control surfaces, and so on and so forth. And this is an instance of the demonstration flight that proved the 81.5 hours. So Philip here shoots the UAV, and afterwards it's an autonomous operation that lasted for all these hours. Of course, it was a boring mission. It was 81.5 hours making the same loop around and around and around. But it was very rewarding, and seeing the plane with its strobe lights overnight was a very, at least for me, in robotics, you probably enjoy science, you enjoy algorithms, but hopefully you also enjoy field work. And this particular experiment was very inspirational in what we achieved, and it was the work of many, many people to achieve it. The important thing is that in the early morning, we had something like 30% of remaining battery, which means that we will be able to do it at different geographical latitudes, at worse conditions, at other parts of the year, and so on and so forth. So when we initially started this project, the estimation was that it would be much more challenging than what it ended up being. Of course, the process was more challenging than what we thought, but the capability to essentially demonstrate multi-day flight was possible and quite quite working at the end of the day. Here you see the strobe lights every 1 second for us to have an understanding that the robot is actually flying and not being lost or something like this. So then we use these capabilities to do large-scale monitoring. So there were a couple of projects in Europe, Icarus and Sherpa, among others, that wanted to survey large environments and do mapping of those. And for those, we had DEMs, digital elevation maps, that we could exploit a priori to afterwards find the full coverage path. So what you see there is the plane essentially performing these missions, and what you also see is a post-process point cloud, therefore it also looks very good from high altitude, that we then provide search and rescue personnel to evaluate if they think this is something significant for their work. And all of them came back with the feedback that this will potentially accelerate how they deal with environments that just now something happened, like an earthquake. And some of this work were also deployed, not with the airplane, but with a multicopter to Bosnia-Herzegovina. There was the flood there, and they tried to detect landslides about where mines are going to go after the landslide. Results are open sourced, and datasets are also open sourced here. And this next video, the only thing it demonstrates that with the same UAV, what you see there on the left is the sensor pod. We also had the thermal camera, and some of my colleagues afterwards worked on victim detection from 100 meters and 150 meters altitudes with a Tau-2 core thermal camera that has a VGA resolution I'm sure you're familiar with. So maybe I shouldn't run the whole video because it will take a while. And I can't seem to be able to play it faster here, so for the moment you have to trust me that thermal camera is there. Now, before finalizing my talk today, I will say that although I appreciate robots that run autonomously, and I hope I can contribute into this direction, I'm sure you will also contribute a lot in this direction. We will all see that in our lifetime that robots will perform autonomously. It's still the case that robots should work together with humans in some aspects. We are still very good in terms of cognitive tasks and so on and so forth. So why not trying to put that together? And many people have worked on that. I'm not in HRI or something like this, but what I want to demonstrate simply is why not using a virtual reality interface like smartphone with a cardboard style of interface to inform the user not only about how the environment looks like, but how our 3D mapping progresses at the time, and then allow the user to use his head motion to adjust the robot trajectory. So we have a predefined inspection trajectory computed with a method presented before, and then the robot performs the trajectory while the user is able to move his head to essentially change how the robot is perceiving the world, to potentially see a particular subset of it that hasn't been perceived before. That's a pretty simple work, and it was also the work of some students and postdoc of mine the first month in my new lab here in the United States. As mentioned, a lot of work went to open sourcing. So the structural inspection planner, the next best view planner, the link for the new planner that we are releasing very soon, many data sets for the structural planner, the next best view planner, the receding horizon, belief space-based planner, so the solar powered UAV with thermal data, with also essentially exploring a national park of Switzerland there. Change detection also, if you perform 2 or 3 missions with the same trajectory for the same space and try to identify what has changed. So we're also working on that actively now to release more data and new methods for change detection. And about what is next, or what I'm planning to do the next period, these are some areas of interest. One of them, I know many of you and your team here at CMU has a lot of experience about exploration in visually degraded environments. What you see here is a picoflex sensor, more or less like a small time-of-flight USB-sized sensor that we turn the lights off and you see the exploration result. Here it's handheld, so it's not UAV, but we plan to do that within November with an experiment with a UAV. Here you see a near-IR camera with IR synchronized LEDs using the same localization pipeline, so robust visual inertial odometry, that's how the paper is called, that performs localization here, and here you see the uncertainty of the robot. It increases, not equally robust with visible light at good conditions, but at least it works, and that's an encouraging sign. Change detection. So the goal here is to essentially, we perform the first mission in the same area with autonomous exploration, and then we recorded this mission, so we are repeating this mission afterwards. We do have a small calibration step in the beginning to make sure, because we don't have a global external tracking solution, we are not using, there is a vacuum system, but we are not using it there at all. So we calibrate the pose in the beginning, and then the robot found the change, and the change was a poster of Yoda from Star Wars. So the whole goal of the robot was finding Yoda, finding where Yoda was placed in the environment, and we did a small object recognition step at the end to find the particular poster. Semantic exploration, given that you identify semantics, again, some work that Your institution has done also a lot. Why not using this information and explore the world in a more reactive way? For us, for human beings, the world is not equally important. Some geometry on a white wall is essentially unimportant. An object or a human being is very important. So why not exploring based on semantic classification and essentially have semantically enhanced path planning? And here what you see also multimodal mapping. You see essentially a car navigating with LiDAR and cameras fused together for this task. And the final thing, which I have absolutely no experimental results and no work in my lifetime apart from my master thesis back then, is multi-robot exploration. And here we just use, we have some people at ETH also open source a simulator called Rotors, and then we integrated our planner so that you have examples that already allow you to test our planner for one or many robots with a particular simulator. So now you see 3 robots exploring the same room environment. And of course, that's in simulation. Things are easier in simulation, but also it allows you to do some systematic testing before going to the real world. So from my side, that is the presentation about autonomous exploration and mapping. I would like to thank you again for hosting me today and attending the lecture, and I will be glad to answer any possible question. Thanks a lot.
So for your things like your bridge inspection, having some rough prior, how does that change your exploration strategy?
Some model prior?
Yeah.
Right. So this is also something that we're working now. So we now consider the case that our prior might exist, but not perfect. So what we do, we have a global set of viewpoints, but every time that we go from one viewpoint to the other, now this is a small set of viewpoints, every time that we go from one viewpoint to the other, we run an instance of the next best view planner, or the receding horizon planner. So now this is the way that I think the first way I have thought about how to combine these two methods. The fact that we can locally explore, and then afterwards essentially also exploit the existing possible model. Now, the next step will be to identify what has changed and only explore around the area that has changed. That's the work we are trying to start now with change detection, a new part of our work in mapping. Yes?
So in the work where you were generating trees using RRTs, I assume, and then selecting one of the branches. The problem with generating a tree is that you can always have neighboring viewpoints existing on totally different branches, and they'll never lie on the same branch again in terms of how a tree is generated.
Yes.
And there's a potential of a rewiring step there as it is done in RRT star. So why not use an RRT star based
Yes,
tree?
we had 2 reasons for that. The part that will increase the computational cost there is doing rewiring while maintaining visibility. Maintaining visibility means that you have to go through the surface manifold that you inspected just now, and maintain that when you do the new rewiring, this thing is again the same. If you don't do that, then you can't evaluate optimality of the branch. So of course that's possible. We did that in this third work that I presented, RRTOT, the forest, essentially the tree of trees, that we did this work. We found that the benefit is small compared to the computational cost that we apply at the end, and how many iterations the tree has to run in order to be able to do new connections like this that don't break visibility. Yes?
Consider integrating in your planner some sort of physics understanding of the world, and in your next test you maybe take into account that. So for example, if you have a reflective surface that's not very good for your sensors, then you might be able to choose a position that helps reduce uncertainty.
Right. So a reflective surface for our sensors will probably mean something bad, right?
Yeah.
So there are 2 things. For those that we have tracked already, for the reflective surfaces that have been part of what we have covered already, this will be covered from the fact that the landmarks on this surface will not be good or not existent at all. Now, for what we hope to do in the future is, if you assume that you have some prior knowledge, as mentioned, because for those that you have inspected, it's actually covered from the belief propagation of the existing landmarks. But if you have some knowledge a priori, what could do is the following: is sample a viewpoint in the future. If you have a 3D model, get the corresponding projection of an image that will correspond if you are to perceive this part of the structure of the particular viewpoint, and then exploit exactly what you say, and broadly this knowledge further. But that will assume that you have some prior knowledge a priori. There are people that are working on that. I know one work from University of Zurich that they work in this direction, but they assume that they have a 3D map loaded on the memory of the robot, and then the robot essentially finds the projected views from one or the other viewpoint. Yes?
I don't know if I missed this, but could you tell how was the uncertainty calculated when you started creating the map, like for every box? How did you get to know what the uncertainty estimate was?
So the robot runs essentially odometry, so visual inertial odometry. right? And then it has the tracked landmarks from the camera system. So it selects, let's say, the 25 more characteristic features that it finds. Those are treated as landmarks in the localization pipeline, and the covariance matrix of those, according to the robot state, are together fused in order to be able to get a covariance of the robot state and the tracked landmarks. So this is the uncertainty for the robot pose and the tracked landmarks, which is different from the probability associated for each voxel. The probability associated for each voxel for the octomap is related with checking that this is occluded or not by raycasting there. So it's two different probabilities associated to one and the other. Any other question?
So what's the trade-off in having the receding horizon? It will depend a little bit on the environment, right? How hard the problem is.
So next best view methods are known to perform well for object recognition, but also known to be myopic about how they select views, and known to give a hungry behavior in the beginning about exploration, but then be very limited on non-convex structures, number one, and also in large volumes, because they always explore towards the frontier, towards where they are. So the next best view exploration is not really only about the receding horizon part, but rather about spanning and finding a path that leads you towards a maximum information gain along all its distance, so with multiple viewpoints. Then the idea, we could also run this one altogether directly. That would be more like open loop. The idea was to run then first on the first step and reiterate to see if this path that we sampled keeps being good given the new knowledge of the map, given the feedback. So one step next best view, which is the classical way that people use, are good for limited environments, small scales, and relatively similar objects, but they're not good when the object has complexity, and they're not good when the system operates in large scale.
Right. So but what's the trade-off in terms of horizon depth? Right? I mean, of course, computation goes up, but we could try to search much deeper and use the...
I wouldn't... Right. If you actually go to the computational cost, that's probably far away here, but it's not really the computational cost that increases. Spanning a larger tree, compared to all the processes we are doing here, especially for the work with belief propagation, spanning the tree is very low cost. And with the way that we are doing about running only the first step for belief propagation, it also does, spanning a larger tree for the first step has absolutely no impact in the second algorithm. So these are the computational costs. So the RRT construction, you can build as much as you want. It's still a very low cost problem. Also, collision checking is also very low cost. So I would say the limit mostly comes from how much can you trust your robot by sampling viewpoints further and further in space. Computationally, we didn't face in the first planner that doesn't do belief propagation any case that environments will require more than very few milliseconds to run. So of course there is a trade-off, and that's the trade-off regarding the computational cost up there on the left and on the right. So if you sample more, you have the number of iterations multiplied by the logarithm of that. So this is how the computational scales. And of course, you benefit in terms of information gain, but you have to assume that the world is always mapped correctly, which is an assumption that doesn't really hold in real life experiments at the end. And once we use this methodology, the second level is not influenced at all from this trade-off, because it will, in any case, only sample for the next viewpoint.
And it seems like the more you know about your world, the longer your horizon would be, right? If you have some patches of unknown, right? The more you benefit from having some...
So one good way will be to somehow couple the probability of how well we know the map to define how far away we can search. Because geometrically, we are not influenced much computationally. We are influenced from what you say, but we haven't done that yet. We haven't coupled the probability of the map with the correlation of how far away we can sample our trajectories. But that's right, and we probably should do it. Further question? Yes?
So in daytime flight, it's not always bright sun. What is how much cloud cover can you tolerate before you don't have enough sunlight to charge the batteries? You need all the electric power to overcome the drag.
Right. So I can't remember the numbers exactly from the paper. The corresponding paper is at ICRA 2016. And what we have evaluated there is not really the cloud coverage. What we have evaluated is the amount of sunshine over the day, the sunshine conditions based on geographical latitude, and also the duration of sunshine for, let's say, July, 15th of July, and so on and so forth. So with the calculations we did back then, and the estimates we had about our propulsion system, because all this at the end of the day is also an estimate about how much power you consume and how much power you are going to gain. And also the calculations we had about our MPPT tracker, because the solar panels are pretty well modeled The MPP tracker was designed by us, so there is a limitation in modeling there. Anyway, what I want to say is that what we found is that from the end period of June to the beginning of August, this mission will be possible. But what we saw experimentally is that our estimates were actually larger. We underestimated the performance of the robot. And we didn't have the perfect sunshine. There were some clouds. It's Switzerland. You can expect some cloud to be around. What I want to highlight is that A, we underestimated. The geographical latitude of Switzerland is very good. It has a large daytime during July. So it's not, here it's the equivalent of, let's say, of Seattle or something like this. So you can do it at any place of the world, maybe. But with these estimates, I believe we can do it. For example, we evaluated we can do it in Mediterranean and other parts of the world that have maybe good sunshine but shorter day. It's not an exact number, however, I know, because it has to rely on many assumptions. And there is also other work from other universities. I know UMN, Minnesota, is working in this field, and they come with different models. So possibly they also have some corrections in this direction. Yes?
Actually, I had a question, Kostas. I might have missed this a bit earlier, the way you formulate the exploration. But for big environments, when you're doing inspection, do you do anything to explicitly avoid sort of drifting off into empty space?
Yes. So there is one term there which benefits small paths. This term is this one. There is an exponential here. Lambda is a tuning parameter. C of sigma is sigma is the path. C is the cost of the path in time or in distance or whatever. And then here we penalize going arbitrarily further away because it's mostly because we put that because mostly for mapping performance. But essentially this will limit you from going into nowhere, into the arbitrary empty space. Does that answer your question, or?
I think so, yeah.
And if the question is mostly from the mapping side, so about going to empty rooms, empty areas, then this planner will not account for that, because this is a volumetrically defined planner. So as long as it finds volume, it will still eventually go in that direction.
Yeah.
Also, the other formulation of the planner, which is this one, it's work ongoing, so some of the questions are answered in one or the other formulation, but not globally. But this formulation of the planner cares for surface manifolds. So if it's empty surface with empty space without any surface, just the ground floor, then this will be avoided, and other areas that have structure will be favored from the planner.
Okay. Let's thank our speaker.
Thank you.